All right, so we left off just kind of talking about, how this document classification will work, and I think there's still a lot of questions about how the maybe multinomial, binomial, and Dirichlet and beta distribution kind of all work together. Okay. So you can think of the binomial distribution has parameter, we'll say it has parameter theta, and technically also 1 minus theta, okay? It's got parameter theta, but that also defines the value 1 minus theta. And this is going to be kind of the probability of yes and the probability of no, okay? And so when you have, your data comes in yes, yes, no, no, yes, no, yes, okay? This becomes 4 yeses and 3 nos, and then you'd have theta to the 4 times 1 minus theta to the 3. Okay, so that's the binomial distribution. The multinomial distribution is similar, okay? Okay, except it has multiple categories. Okay, and so you might have some vector theta to represent, you've got theta A, theta B, theta C, theta D, theta E, or something like that, okay? And then your data comes in, and so this is the probability, and then you have basically the sum of the theta values will be 1. So this is, the probabilities of the 5 different categories so that everything adds up to 1, and your data might come in as, A, C, E, C, B, D, A, C, okay? And so this sums up to 3 A's, 1 B, 3 C's, 1 D, and 1 E. Okay, and so your probability here is going to be theta A raised to the 3rd, theta B raised to the 1, theta C raised to the 3rd, theta D raised to the 1, and theta E raised to the 1. Okay. Or we might write this using, when you read up on the multinomial distribution in Wikipedia or some other, how does this work? Let me look up the help. It just writes it this way, but the PMF can be written as basically some coefficient times the product of basically theta sub, in R we have theta sub j, or p sub j raised to the k sub j. Okay, so this is kind of your vector k is the counts, and this is going to be j from 1 to, what letters do they use? To capital, I guess capital K. I guess this is your x's. Okay, and so this is what we have in the homework. This makes an appearance in the article. You have on page 16 equation 49. At the end you have the product from I equals 1 to v of theta sub x comma I raised to the w j comma I. All right, and so here here we had 5 categories. Here it's theta is a vector of length v. Okay, v is how many words are in the vocabulary. Okay, I think for the homework there's something like 59 words in the resulting vocabulary. Okay, so rather than just having categories A, B, C, D, E, you've got word 1, which is fox and box and house and mouse and whatever it might be, and then you count how many times. So W sub j is the vector of word counts. Okay, so also length 59. Or also length v, okay, and it's how many times did that word appear, okay? And so you can do this, you can do each theta raised to the w. This can also be achieved, can be calculated with R's d multinomial function. Okay, and so here you would put the vector of word counts, for for the document J, and then you'd have probability equal to theta 0 or theta 1. Okay, and so this will calculate, when you use this, this will calculate the likelihood of your data, of this vector of word counts, given the current probability vectors theta 0 and theta 1. So it'll say, if the document was of class 1, what's the probability of getting this word count? Versus if the document were of class 0, what's the probability of this word vector, right? So this basically says, if the label LJ is equal to 0, what is the probability of our document word count? Versus if the label LJ is equal to 1, what is the probability of our document word count? So the word count is a vector, in our case, of length 59, because we have 59 words in our vocabulary. And we take each of these theta values, which add up to 1, and we raise them to, how many times did that word appear? Okay, so what's the probability of the word fox for documents of class 1, and how many times did the raised to the time, how many times did the word fox appear in our document? Does that kind of make sense? So if I have a simple, so we'll just simplify this, and let's say I've got fox and box and green, and dog and car and boat. Okay, maybe this is document 4. Document 4's word count vector. If we only have 6 words, right? And so we can say this 10, 5, 6 and 0, 1, and 2. Okay. And then we might have somewhere else, we might have theta 0 being fox, box, green, dog, car, boat. These probabilities, I'm just making stuff up here. I've got 0.2, 0.2, 0.3, 0.1, 0.05, 0.05 versus theta 1. Maybe this, we're at 0.1, 0.1, 0.1, 0.3, 0.2, 0.2, or something like that. Okay, and so if we did d multinom of W4 and theta 0, this is basically 0.2 raised to the 10 times 0.2 raised to the 5, 0.3 raised to the 6, 0.1 raised to the 0, 0.05 raised to the 1, and 0.05 raised to the 2. And we compare this to d multinom W4 given theta 1, which is going to be 0.1 raised to the 10, 0.1 raised to the 5, 0.1 raised to the 6, 0.3 to the 0, 0.2 to the 1, and 0.2 to the 2. Okay, and we would get numbers. Yes.
So the theta 0 doesn't add up.
This theta 0 doesn't add up to 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Oh, you're right. Okay. Here, I'll do 0.15 and 0.05. Is that okay? All right, there we go. Now we're fixed. So they should add up to 1. Okay. Okay, so this is what we have, and we compare the and we compare these. So this is kind of the likelihood of our data if it belonged, if this document, right? So these are the word counts for document 4, and this is the likelihood of data if LJ equals 0, and then this is if LJ equals 1. So if the document belonged to class 0 versus it belonged to class 1, okay? And you don't have to do this. You can do d multinom, and this is what the computer's doing, right? Is that okay? And d multinom also, puts in the coefficient in the front and stuff. So this part in equation 49, this is equal to this part of the vector, okay? That's what we have. The Bayesian classifier here says, we're not going to just look at the relative multinomial likelihoods, okay? We have to take into account how many documents are in class A versus, or class 1 versus class 0, okay? So, in our case, we have 19 documents, but, you can imagine a scenario where you have 100 documents and 90% of them are class 0 and 10% of them are class 1, okay? So the prior distribution, before you actually look at the probabilities of the words, right? If you just know in the corpus, if you just know ahead of time that 90% are currently labeled 0 and 10% are currently labeled 1, before you look at the words, I say guess, make a guess for the class of this thing. You would say, well, it's going to be class 0 with probability 0.9. Okay, that's the prior probability, and so we need to weight the kind of that prior information in here. Okay, so we have the likelihood based on the words that show up in our data, but then the prior probabilities of a class label depends on you know, the proportion that exists in the corpus right now. Okay, so you know, maybe, so you know, we have n equal to 19 documents in the corpus, okay? And maybe we'll just pretend our current assignments say C0 is equal to 12, so 12 documents are labeled 0. And C1 is equal to 7. 7 docs are labeled 1. Okay, so our prior probabilities you know, depend on these proportions. Okay, we will take into account the hyperparameter. Okay, so we also include a pseudo count ahead of time. So rather than just saying 12 and 7, which you know, which can shift anywhere from 0 to 19, we also include the pseudo counts, which kind of define our are used to define the beta distribution. Okay, so you know, we said beta pi comes from beta phi 5, which turns into gamma pi 0, which is basically our shape parameter alpha, and gamma pi 1, which is our shape parameter beta. They're both equal to 5. And so it turns out, you know, equation 49 simplifies all of the math. And we get kind of the prior proportion, including pseudo counts, to be C for class 0 is C0 plus gamma pi 0 minus 1 divided by n plus gamma pi 0 plus gamma pi 1 minus 1. Okay, so in this case we'll have 12 plus 5 minus 1, and this will be 19 plus 5 plus 5 minus 1. Okay, and then for class 1, we have C1 plus gamma pi 1 minus 1, and n plus 5, n plus gamma pi 0 plus gamma pi 1 minus 1. And so this gives us 7 plus 5 minus 1 and 19 plus 5 plus 5 minus 1. Is that okay? So these are kind of the prior proportions when we include all of this stuff. So this is, this is also all from equation 49. Okay, and so anyway, this is going to give us kind of relative probabilities. This gives us relative probabilities, and we'll do basically one is going to be value 0 is equal to equation 49 for class 0, and then value 1 is equation 49 for class 1. And then basically you scale these, so the probabilities add to 1. Okay, and so you're going to get val 0 divided by val 0 plus val 1, and then val 1 divided by val 0 plus val 1. Okay, and then part 4 is now we randomly sample our label LJ based on these values. Okay, so maybe we get val 0 equal to 0.004 and val 1 is equal to 0.001. Okay, this is just a silly example, and so the probabilities, you get 0.004 divided by 0.004 plus 0.001, which becomes 0.8, and then over here you have 0.001 divided by 0.004 plus 0.001, and you get 0.2. Okay, and so this LJ is 0 with probability equal to 0.8, and LJ is 1 with probability equal to 0.2, right? So what do we do? There's a few ways you can do this. One is you can just draw U from uniform, 0, 1, and then if U is less than 0.8, then LJ equals 0, and if U is greater than 0.8, LJ equals 1. Okay, and so once you have achieved this, then you now you are done for document J, and then you move on to the next document, right? So finish for one document. Okay, move to the next. And now this requires you must recalculate the count of documents labeled 0 and the count of documents labeled 1. Okay, so you'll complete that. And then so you'll have new C0 and C1 values. Is that okay? And then you do this, so each time you update a document, your C0 and your C1 changes, okay? If the label of the document changes, then C0 and C1 change. And you have to, and then so the next document that you sample is based on, the new counts, C0 and C1, okay? And then, you keep updating them accordingly. taking into account, these values of C0 and C1, and taking into account, theta 0 and theta 1. Okay, so you use those things, and so now after you go through all 19 documents, or however many documents are in your corpus, now you have kind of a new corpus of documents labeled 0 and a new corpus of documents labeled 1. Okay? All right, is this part okay so far? All right, and then so now the last part is, so you recalculate this, new documents. Okay, so you do this for all documents in the corpus. And then when you are done, okay, when you are done, you now exit the inner loop. Okay, we need to draw new values of theta 0 and theta 1. Okay, and so theta 0 will come from a Dirichlet distribution given a vector t0. Okay, and theta 1 will come from a Dirichlet with vector t1. Okay, t0 is just equal to the total word counts for all docs in class 0. Okay, and so let's say so this is document 4, right? So let's say, okay, so we'll say L4 is equal to 0 and L5 is equal to 0. Okay, so I'm going to just make up another word vector for document 5, and maybe this is 8, 7, 3, 0, 2, 4. Okay, and then let's say these are all the documents, all docs currently labeled 0. Okay, so then your T0 is going to be 18, 12, 9, 0, 3, 6. Okay, so it's just the total word counts. So for all the documents currently labeled 0, Fox appears 18 times, Box appears 12 times, Green appears 9 times. Okay, so we're just creating a total word count vector for all the documents currently labeled 0. And we use this to generate our theta 0 value. Okay, however, having a 0 in your this creates a problem. Okay, having 0 is a problem. Okay, so we add our pseudo counts. Okay, and so I think I just have theta gamma theta equal to 1. So we just add 1. So T0 becomes 19, 13, 10, 1, 4, 7. Okay, so we add pseudo counts. We just add 1 to every cell. Okay, and then we use this. Theta 0 is drawn from the Dirichlet with T0. Okay, and I saw in Piazza, how does the Dirichlet work, right? How does the Dirichlet work? Okay, the answer is it works kind of like the beta distribution, but for more than 2 categories, okay? And kind of like the beta distribution, but for more than 2 categories. Sorry. Okay, so how does the beta work, right? Like if I have beta 5 comma 5, what does this look like? So the beta goes anywhere from 0 to 1, and what this says is 0.5 is most likely, but we'll also accept, it's kind of like saying, so the beta distribution, you have to think of it as I've got some mystery bag with marbles inside, and we draw marbles with replacement, and we see 5 red and 5 blue, okay? What is the proportion red in the bag? Okay, that's what our beta 5 distribution says, okay? If we have a beta 500 comma 500, what does this look like? Beta 500 500 anybody? It's really tall at 0.5, right? So it looks like this. Something like that, okay? And so this basically says, we see 500 red and 500 blue, and what is the proportion red? Okay, and the answer is, in both cases, 0.5 is the most likely value. But when we only have 10 observations, P equal, or theta equal to theta red equal to 0.7 is is still kind of likely, while with 1,000 observations, theta red equal to 0.7 is very unlikely. Right? So that's how the beta distribution works. You put in kind of your pseudo count of how many red and how many blue you've seen, and it'll say, okay, the proportion of red is this, and it looks like this, right? And so if you have beta, let's say 80 comma 20, then from 0 to 1, we're going to be centered at 0.8, and we've got 0.8 is most likely, but 0.85 is also possible. Okay, so that's the beta distribution. The way the Dirichlet works is your bag of marbles no longer has 2 colors, it now has K colors, okay? And in our case, we've got 59, words, okay? 59 colors in our bag, all right? And so, just for simplicity, so for the Dirichlet, okay, instead of 2 colors, you know, we have k colors, right? And so Dirichlet, let's say 20, 20, 20, 2, 2, 2 says, here, wait, let me just get everything to add up to 100. So, so I've got 6 over here. What's 94 divided by 3? Here, we'll just change this 90. So we'll do, sorry. So I'm going to do 32, 32, 32, and then 2, 1, 1. Okay? So I've got, you know, 100 observations, 32 times we got, what were the words I was using? Fox and box and green? I don't remember. Fox, box, green, dog, car, boat. Okay? Fox, box, green, dog, car, boat. Okay? And so what this will produce is it's going to produce 6 theta values, right? And so theta 1 will probably, if we look at the distribution of just theta 1, this will probably be centered somewhere around 0.32-ish, okay? Something like this, okay? And if we looked at the distribution of theta 2, it would also be centered around 0.32-ish, something like that. And then, and this one for theta 6, or I guess I should call this theta fox and theta box and theta boat. We're going to have something that looks like this, right? Meaning the probability theta boat is going to be something that looks like this, right? Whereas if I do Dirichlet so it adds up to 100. Okay, so if I do 20, 20, 20, and 13, 13, 14, does that add up correctly? I think. Okay. So here, if we look at the distribution of theta fox, you know, what is this going to look like? Okay. So it can be at any value from 0 to 1, where 0.2 is most likely, but we're going to have quite a bit of spread here, right? And over here for theta boat, you know, going from 0 to 1, you know, probably 0.14 is most likely, but also quite a bit of spread. Okay, whereas if I have Dirichlet, now we're going to do like 2,000, no, I'm sorry. Well, what did I say? 3,200. Let's just take it to the extreme, okay? So we're going to say like 3,330, 3,330, 3,330, and then I want this to add up to 10,000, so we'll do, you know, 30, 30, and 40, okay? So now the distribution for theta fox for between 0 and 1 at 0.33, we're like very confident that it's going to be at 0.33, right? Because this is, we have 10,000 observations and we saw fox appear 3,330 times, okay? So now we're very, very confident that the probability of drawing fox is something like 0.33, okay? Whereas over here, theta boat, you know, between 0 and 1, we're pretty, there's just a very narrow spike at 0.4, and we're pretty sure it can't be, you know, much else than that. Does that kind of make sense how this Dirichlet works? So it's basically like the beta distribution, where the beta distribution will say, you know, based on how many red marbles and blue marbles you've seen, and you want to kind of create a distribution of what's possible for the proportion, we're doing the same thing. We're creating what's possible for the proportion, except it's a proportion of one of many categories rather than just red versus blue. Now you've got 6 categories or 59 categories, and they all have to add up to 1, but so you're getting this kind of distribution, and if you've seen a lot of a certain value, then that means you're quite confident about the proportion that you're getting there, okay? And so what we're doing is we use the number of times we see each word as our pseudo counts that define our Dirichlet distribution, okay? So we have theta 1 coming from here, and we have theta 1 coming from the Dirichlet using the pseudo counts from documents of class 1, okay? And so we use that to produce a new random draw of theta 0 and theta 1, and once we produce those new random draws of theta 0 and theta 1, we cycle back to the top of our Gibbs sampler, and we draw new values of L, the label, for each document based on the words that appear in that document and the current values of theta. Okay. I know it sounds like a lot, okay? I promise it's doable, okay? I had some students come to office hours today, and you know, they had some trouble getting some stuff working, but I just nudged them along in the right way, and they got it working within office hours, okay? And so, you know, you can try it and you can code it, and when you get it to work, I think it's pretty neat, okay? That these unlabeled documents will get sorted into their proper categories, okay? And also, our data, the documents that we're using are so, they're very simple, right? They're children's books, and so with our Gibbs sampler, it will actually successfully sort the documents probably within 10 iterations or so. You only needed a handful, just because the documents, the vocabulary is only 59 words, there's only 19 documents, and this contrast between the document classes is quite stark. And so it only takes a few iterations, or you know, less than 10, to get them to sort properly. Okay, but you know, this can then be generalized to, you know, larger corpuses of documents with larger vocabularies as well. I've you know, based on kind of what happened in office hours, I've updated the R Markdown template on CCLE, just the part where you write your code, and I've kind of made some I've made a few changes, because originally I based my comments based on the pseudocode that was provided at the very end of the article, and so there are a few things I changed. It'll match a little bit more closely to you know, what I've said here in lecture, and I think you should all be able to code it up and do it. Okay, so please you know, try it out, work on it yourself. Okay, don't just copy someone else's work. Okay, I want you guys to enjoy the satisfaction of solving it yourself. Okay, I will talk about the final exam on Friday. Okay, so on Friday we'll talk about the final, and I'll see you guys then. Okay.